Welcome back. In this video, I'll show you how to change simulator settings in Drake and configure your logger to publish data at periodic time intervals. We will also review the motivation behind variable time-step integration methods and why Drake uses them by default. First, let's review error-controlled integration schemes. Computers numerically solve differential equations using numerical techniques. The simplest method to solve an ODE is Euler's method, which you might remember from your calculus class. More advanced methods such as RK3 are commonly used instead, as they obtain better approximations of the simulation at the next time step. I might do a video on how RK3 works if there's enough interest, so leave a comment below if you'd like to see that. RK3 is the default integration method for the Drake simulator. Regardless of the method used, choosing an appropriate time step is very important for ensuring fast and accurate integration. If the time step is too large, the error could be very large. If the time step is too small, the simulation will take forever to run, and also there'll be so many steps that numerical roundoff error will build up and affect the simulation accuracy. For many differential equations, a large time step might work most of the time, but there are critical times in the simulation where a small time step is required. For example, if you have a pendulum near the vertical equilibrium point, the simulation will need a small time step to capture the dynamics correctly. Because of this, there's often no good choice for a fixed step size, so we use an algorithm to dynamically choose the step size in order to balance speed and accuracy. By default, Drake uses the RK3 solver with a variable time step. In this video, you'll learn how to change the simulator settings. Now let's look at the logger that we normally create with the log vector output function. Until now, we've ignored the publish period argument. Without specifying it, the logger will publish at every time step. If we specify the publish period to say 1/60 seconds, then the logger will publish data 60 times per second. This might be useful, for example, when creating animations. On the next slide, you'll see the difference between ignoring or using the publish period argument. I ran two simulations and plotted the difference in the time steps. The one on the left is when we didn't specify the publish period, and you can see how the time step changes. On the right, I specified a publish period of 1/60 seconds, and we can see how all the time steps are the same size. Now let's move on to the simulator config. This is a struct that we use to set different simulator settings via the apply simulator config function. You can see the documentation in the top right corner, which specifies the different attributes that you can set, and also some Python code showing how to actually set these values. The list of integration schemes can be acquired by printing the output of the get integration schemes function, and you'll see this code in the starter code later. Most of the attributes are self-explanatory, but I wanted to highlight the use error control and target real-time rate attributes. The use error control attribute dictates if you want to use error control or if you want to use a fixed time step. I recommend leaving this attribute alone, but in the next slide, we'll see what happens when you play with it. The target real-time rate attribute will insert delay between simulation steps so that it runs in real time or at double speed or whatever speed you set. In later videos, we'll use this for creating animations. In task 2, you will explore using fixed time steps for a pendulum plant. These plots were generated by my solutions to that task. In blue, we have a variable time step solver. The other colors show the output of different time steps. What's interesting is that the green line, which uses 10 millisecond time steps, is closer to the variable time step solver than the orange line, which uses 1 millisecond time steps. This is because the variable time step solver typically uses time steps between 10 and 30 milliseconds for this particular simulation, as you saw in the histograms on slide 4. To help you master the ideas presented in this video, I provided some additional reading along with some tasks for you to try on your own. I have some starter code and the solutions to these 3 tasks provided on my GitHub page. You can find a link to my GitHub page in the video description below. In the next video, we will talk about a unique and extremely powerful feature of Drake, which is using AutoDiff to linearize a leaf system about an equilibrium point. This is extremely helpful for creating model-based linear controllers such as LQR. If you found this video helpful, be sure to leave a like and subscribe so you don't miss the next video in the series. Leave a comment if you have any questions or if you have another video request. See ya!